Okay, so today we're talking about statistical significance and why that concept on its own is really not sufficient for decision making or action. Uh, I see it all the time in research articles or news articles or pharmaceutical commercials or something like that. You hear there was a significant relationship between uh, these two variables, these two treatment groups, or something like that. And uh, the implication being, I think, is that it's supposed to matter to you. That the fact that they're statistically related means that it is important. But that's really not the case. All statistical significance is telling us is that uh, the amount of signal in the data relative to the amount of noise is sufficiently large to basically conclude that that signal is real. But it doesn't tell you actually anything about how big in magnitude that signal is. So it's possible, say, with large enough sample size, to have the tiniest difference between groups and still get statistical significance. And you might also have really large differences between groups, but there's a lot of noise, maybe small sample size, and you don't get statistical significance. And so this article is really just a high-level overview, a case of simulation, just to kind of show why on its own statistical significance doesn't really matter. It needs to be context dependent. You need to interpret the magnitudes of the effects that you're finding, and kind of use subject matter knowledge and domain expertise and things like that to interpret the results for what they are, not just whether or not they cross some statistical threshold. And so the focus here in this video is going to be going through the R code, mainly that generated the different plots, and all of it's going to be just taken directly from the blog webpage. There's this little button in the upper right corner of the blog post where you can actually find, show all the code, and that's all I'm doing is copy and pasting it there. All right, so we're in our studio, and we're going to run through the code. So again, it's all on the original blog post. You just have to expand those arrows, and you can see all this code. I just copied and pasted it over here. So the first thing I'm going to do is load the tidyverse package. It's basically the first thing I do in any R script, which is going to give me all of my packages and functions I generally work with. So the first thing we're going to do is simulate the data set that's used throughout the entire article. And so we're going to set the seed to make sure we can reproduce our results. And so if you remember the context, we're looking at kind of the average sales by customer age. And so we're taking a sample size of 500, and here's where we're actually creating the data set. And so this is really where all the results that you see throughout the article are based on. It's based on what's defined here. So first we're generating the age distribution. I used this R gamma function. I wanted something right skewed. I was thinking I just wanted something where most of the customers were, say, in the age range of like 20 to 40, and then you have some upwards of like 60 and 70 and 80, but it was right skewed in that direction. So I kind of just played around with the parameters until I found something I liked, and then based on that age, constructed the models to generate the sales that we use in the plots. And so this is where we are really defining kind of these two models, where we see in the first plot basically the same relationship, when we see the same amount of statistical significance and everything, but it turns out that they are vastly different effect sizes, even though statistically they are virtually identical. And all this really is defining what you can think of as the true linear regression equation that we would be estimating with data, between age and sales. And so you can see age here, and we're generating sales amounts as a function of age. Both of these have an intercept of 500, and we are centering the age variable at the mean. So we're basically saying both of these are going to have a average sales of $500 per customer at the mean age value, and then everything else is kind of varying from there. And so it all has to do with the slope and the standard deviation in the random noise. And so in the plot where we see kind of the larger effect, where it's actually something probably meaningful, is we have this 10 here, which is the slope, and it's saying that for every 1 year increase in age, our average sales increases by $10. And so you can think of this also as for any 10-year age difference, the average amount of dollars spent per customer is $100 difference. And so in many cases, I would think that's probably something practically meaningful. But then when we look at our random error term, there's a standard deviation of 100. So at any given age, like at the mean age, we're saying there's an average of $500, but it's going to give or take a couple $100, and that's kind of the distribution. So there's quite a bit of variability we might observe between, say, $200 spent and $800 spent or something most of the time for the mean age, and it's going to obviously change depending on the age. And so, but one thing to notice is the this rough signal to noise ratio. So the slope is 10, standard deviation of 100. So the slope is 1/10 of the standard deviation, and not that that necessarily matters, but in comparison with the other model, it kind of does. So you can see again the same intercept, but this time we have a slope of 0.1, which is saying for every 1 year increase in age, we're only seeing a 10-cent increase in average sales. So there is a true effect there, it's just 10 cents. And again, another way to think of that is for every 10-year increase in age, it's $1 difference on average. Again, probably not super meaningful in a lot of contexts, especially when you're saying that kind of the base average for the average age is $500, and you're talking a couple dollars of variation here and there. And so a very small amount of change is taking place here. But if we look at the random noise, the standard deviation of 1 is saying that it's only varying by a couple dollars. So before it was varying by like couple $100 at a given age. Now it's only varying by $1. And so the effect size is very small, but it's also not varying a lot. So if we look at that sort of rough signal to noise ratio again, 0.1 over 1 is also 0.1. And so both of these models essentially produce the same amount of statistical evidence. And for all intents and purposes, they are virtually identical from a statistical perspective. There's nothing about them that differentiates themselves from one another in terms of statistical signal or anything like that. And so this is why it all comes down to the context. Obviously, one of these dollar amounts and the amount that it changes with age matters probably in a certain context, and another one doesn't. But statistically, you could think of these as virtually identical. So, all right. So if we run that, we get our data set. Looks something like that. We use this pivot longer function to pivot our data down, set it up nice for building our plots. And now we're going down to the first plot, which is just, again, the first plot was just this plot with the y-axis labels removed, so we can kind of show that, okay, these things look pretty similar when the scales are removed. So far so good there. And if we want to kind of briefly touch on what we did, so we used the ggplot package, ggplot2 package, and just made this scatter plot, and added a bunch of different settings, formatting settings to make it look nice. And basically the same template is what's used for the rest of the plots. It's just a little additions here and there to get what we want. So plot 2, then we say in the article, okay, now let's fit a line to each of these to see what that looks like. So here what we are doing is first nesting the data, and so this nest function is probably one of my favorite functions in R. And so if we just show what that result is with nesting our data by these different kind of simulated data sets based on the large effect size and the small effect size, we're creating a new data set where instead of like a number in one of the columns, it's an entire new data set in a list within a column. But the beauty of these nested data frames is that we can basically operate on them as we would any other data frame. And like the coolest thing to me is being able to join with these things. So you can imagine having these nested data sets, but then you wanting to do like inner joins with other data sets, and the things that are coming along for the ride in those joins are actual full data sets, and you're maintaining the nesting structure. So this is something I use all the time. Alright, so what we're doing here is within each of these data sets, we're going to use the map function from the per package, and we're just going to fit a linear model to each of these data sets. So we're regressing sales on age, and that's all this chunk is doing. And so it's going to create this column called model, which is going to be a list of linear models for our large effect and our small effect. And then the awesome thing about using dplyr and mutate, even with or without nested data sets, is that we make the model here, and then within the same mutate call, it's now available for me to pass into the next thing. So I wanted to extract what the p-values are for the slope coefficient in each of these models, and so I just calculated them by hand using the t-distribution. And yeah, so if I run this, called it sim models, all we did is append to the data frame we started with here's our list of linear models, and here's our list of p-values, and we can pull out the p-values if we wanted to see what those are. So these are virtually 0, and they're both, for all intents and purposes, the same. We could pull out the models as well, and we can see the intercept and slope that was estimated. Okay, so in the next plot, then we wanted just to add those models to the plots, just overlay the lines that were estimated. We don't actually have to use these model objects that we constructed because ggplot has this geom smooth function, and we can specify method equals lm, and it's just going to fit a linear model within each of these panels and put it on the data, so it's doing the exact same thing. So the code here is basically the same as the last plot, except that we're adding this geom smooth component to add the line to each of those, and we are adding the text of the p-value that we just computed. And so we're doing a little bit of cleanup here to get those, but we're just saying we're going to unnest the data and we're going to pull out the p-value into a non-nested structure and then doing some formatting. So typically if the p-value is really small, we're going to just say it's less than 0.001. And so you could see what that part looks like. Just looks like this. And so we're using those p-values as labels and just putting them in a particular location to make it look nice. Alright, so if we run that, and there you go. Those are the lines. And so, again, still, without the y-axis scales, these things look basically the same. P-values are just very small. The slopes, at least how it's plotted, look pretty much the same. And so the next plot is where we actually add back on the scales to show what's going on. And so here's where you start to see the difference between these two models. Again, we're allowing the scales to freely vary in these panels, so it doesn't really, so they still look the same, but obviously the scales start telling the story that at, say, age 30, customers are spending on average $499, and at age 60, customers are spending an average of $501. And so you go from the lowest stage to the highest stage customers, you're only talking about a few dollars, even though there is overwhelming statistical evidence and again, for all intents and purposes, from a statistical perspective, no difference here on the right side than on the left side. But on the left side, here we see someone who's 30 is spending an average of, say, was that $300, $350, and someone who's 60 is spending closer to an average of $750 on average. And so that's probably, in most business contexts, more meaningful, despite, again, no difference between these things statistically. All right, and then so the last plot is just now putting a stamp on it to say, okay, these are in different scales currently, or these y-axes are varying freely. What if we just put it all on the same scale so you can just see how different they are? And that's what we're doing here. So now we actually have it all on the same scale again, and the left plot is showing this wide range of dollar amounts, and the right plot is virtually flat. And if you saw this and didn't know anything about whether or not it's statistically significant, you would say, well, this doesn't matter at all, probably, right? And so the fact that it's statistically significant shouldn't really change anything about that, except for the only thing being maybe wondering how it's the case that there's so little variability that would allow such a small effect size to be statistically significant. But yeah, in any case, this kind of meant to just put the stamp on the fact that we have two drastically different effect magnitudes, but statistically they are identical. And then the final plot here was just a histogram in the summary of the blog post, just showing the distribution of age. So here's what we generated in the beginning. It's kind of right skew distribution. And the point here was really just to start thinking about what you're actually, like what the implications of making decisions based on kind of these models you're developing are. Uh, so the idea here was maybe there's some sort of marketing strategy where you wanted to target, say, older customers, but because there's so few older customers in your in the market, it costs more to, say, advertise to any single older customer, even though they spend more on average. So then you start to think, okay, well, based on those, the magnitudes of those lines that we saw before, you can kind of start to combine that practical cost benefit analysis of, okay, how much is it going to cost to actually obtain or reach out to one of these customers, and how does that play into or compare with our estimated line. And so if you started bringing in those two model comparisons, you might find that even if it wasn't such an obvious case where the effect size is so small that it clearly doesn't matter, it might be something that's more in the middle, and you don't really know, you might start thinking of something like this where you put these models into these what-if scenarios that say, yeah, we have some sort of meaningful relationship between age and sales, but when we use those models and connect that with our cost-benefit analysis and the actual amount that it's going to cost to implement some sort of marketing strategy, we still find that we're going to be in the loss on average. Like the effect is still not strong enough. And so, again, that has nothing to do with statistical significance. That all has to do with the practical implications and bringing the results into context.